So good afternoon to one and all. I hope it's 2:30 by BST and 2 o'clock out over here in India. So very warm welcome to all the participants. Today we are over here to have a discussion on a special software that is basically used for our power system analysis and power system operation and control. And this particular session, if we talk about, we are going to see the various attributes of a particular software. We are going to see the various attributes of a particular software that is by the name of DLGSilent PowerFactory. So we are over here basically to focus on this particular topic, that is DLGSilent PowerFactory. So before moving into the PowerFactory, let us have a small glimpse of what is DLGSilent and what are the various other products that this DLGSilent provides with. So if we talk about DLGSilent, it is basically an organization which works on the various softwares, which are totally related to the power system analysis, and along with that, there's another part that is the power system operation and control. So thereby we can say that this DLGSilent software gives us a total integrated solution to all the problems related to power systems. So today he is a host, Abhinav this side, and I'll be taking you through the journey of this DLGSilent PowerFactory simulation. So as I said, we'll be starting off with the various products. So over here, we can basically see that apart from PowerFactory, the DLGSilent has yet another important software that is said to be the stationware. So before moving into PowerFactory, let us have a small look as to what is the stationware doing and what is the need of the stationware. If we look into the primitive power systems, based on the load, never the power systems were not that complex before around, let us take it to be 30 years or 40 years. The loads kept on increasing. Gradually, the demand had to be met, and thereby we had more and more generating stations. The transmission system becoming clumsy, and by needed much more advanced software simulation of systems. The answer is certain. Why? Because the results that we are simulating today have to be changed or have to be manipulated as per the requirement in near future. So thereby, we have to have options whereby we can expand the system, we can make much more integrations, and at the same time, we can make this platform a global platform, thereby visualize same time making some important additions or subtractions, or rather change the runtime process. So that made us to come with the software that is the DLGSilent stationware, in which database management part for all power system substation data. So if we move into any substation, we talk about any substation, over there, obviously we are going to find various power system equipments arranged in a particular manner so that the power can be dissipated or distributed. So if we talk about the distribution of this entire system, we have to be very much cautious of each and every equipment that we pick up, the ratings that we are assigning to each and every equipments, the per unit values that we are assigning to the entire system. So all this have to be maintained in the form of a database, thereby to prove as to which were the conditions whereby we entered into a fault, which were the healthy conditions, and whereby the system was running perfectly. If at all there was a short circuit, what was the exact point of short circuit? Where are we making the short circuit analysis? So all these things have to be analyzed and kept in the form of a documentation. So this documentation part was very much important. And in order to manage all those things, we came up with this stationware part. And the backbone of the stationware, if you look into, it is basically the .NET frameworks. The various .NET frameworks helped us to develop this DLGSilent stationware. So apart from this was not a part of discussion of today, but we should always know, if you're studying about a particular, if you're trying to know about a particular organization software, we should also know what are the supporting softwares in this particular field. And thereby came the need of the stationware to introduce you people to the stationware. The other part, which is our point of focus today, or the point of discussion, that is our Power Factory. So what is this Power Factory basically doing? If we look into any power system, the main part that we look into is the generation, transmission, and distribution. So it starts from the generating station and ends with our end feeders or load feeders. This entire journey has to be analyzed and has to be seen whether we are running a reliable system or not. The reliability of the system has to be kept at foremost level. And in order to ascertain the reliability and the power utility of the system, we have designed a software whereby we are working on this particular software where we can add on graphics, we can have graphical views, we can have representations, we can make analysis, we can make advanced studies using this lone software that is said to be the Power Factory. And we have various versions, obviously, of this particular software. That is, Power Factory has various versions. You can work with the Power Factory 14 version. You can work with the 15 version. You have a latest 2020 version. You have a 19 version. Though the 2020 version is still a beta version. It's a beta version. But 19 version, it has been an established version in the market. And all these versions that are coming up are being supplemented with some additive features, some advanced features, apart from the basic features that the software already had. The basic software already had some basic features of power system analysis, but apart from the same, it had some additive features with the progression of its various versions. So far, any questions? I'd just like to cross-check with my speed once if I'm quite audible and clear. If I could have some prompts in the chat box. If you want me to be a bit slower, or if you can match with my frequency, my pronunciation, if everything is okay with you. Can I have 1 or 2 prompts quickly, please? You can use the chat box for the same. Fine, thank you. Thank you for your confirmation. And if you have any questions, I'll be on the slide and thereafter I'll be on the software. So it is a full screen view that you are having. And I hope you're able to see my screen parallelly as well. Yes. So the thing is, if you have any questions in between, please do turn on your mic and you can prompt in with the question. I'll thereby stop and I'll be trying to answer your queries, right? Okay. Moving on to the next slide. These are the Power Factory highlights, the software's highlights that we will be looking into. First of all, it is quite economical and all-in-one solution. Why all-in-one? All the various attributes we are going to see in the succeeding slides, that all the various attributes of power system analysis have been clubbed, have been put into a single software, that is our DLGSilent PowerFactory. So it gives us a coverage of the entire state of art of power system applications. You cannot go beyond this. You talk about LV systems, that is low voltage systems, you get that. You get you want to study your MV systems, that is medium voltage systems, you get that. You want to study your network analysis, you get that. You want to study about your AC transmission, you get that. You want to study about your DC transmission, you get that into your software. If you want to study about your renewable power energy, you also get that. If you want to study about your grouped, that is your grid systems, you get that feature. So it's economical because you are just going for the simulation. There is no hardware implementation into this software, and thereby obviously it is cost saving. Extensive and flexible modeling capabilities with rich suite of power equipment models. Why do we call it to be rich suite of power equipment models is that if you talk about any power system, the first thing that comes to your mind is such generation. And if it is a generation, you ought to have a generator over there. So you have the representation of a generator out over there. Then you have to have the, sir, I have to have a generator bus. If I don't have a bus, how can I transmit? So you have a bus facility out over there, and that bus is not a single bus, a single type of a bus. You can have as many number of arrangements as you want. If you want a main and auxiliary bus arrangement, you'll be finding that. When you move to the software, I'll be showing you those arrangements. You want to have a single, want to have a single line diagram representation, that is the SLT representation, you can have it, right? Apart from that, then comes the transmission lines. So I want to design my own transmission lines. I want to specify the voltage. I want to specify the distance. Accepted. You have option for the same. So I want to have a load connected. Now, what sort of a load? Sir, it is an undetermined load. Now, it is not determined at this point of time. Fine, you can have your load feeders connected out over there, and you can assign a particular load values to the system. That is the active load and your reactive load. You want to have a motor load connected, sir. You can connect a motor load out over here. So any type of load that you want to connect, any type of bus bar arrangement that you want to have, any type of generator that you want to design, any type of transmission system that you want to have various topologies of your network. You want to have your ring topology, you want to have your star topology, you want to have your mesh topology. All these features are easily available, readily available. Just you need to pick and place in your grid system. So that makes your system really flexible, isn't it? Supports all network representations and phase technologies. When you talk about phase technologies, as we have briefed you up, if you are talking about a three-phase system, we can have a three-phase three-wire system, and at the same time, we can have a three-phase four-wire system. So like at the end feeders, if you talk about, we can have three-phase four system as well. So these features are available out over there. You want to have your neutral shorted, it's there. You want to have a single phase diagram, single phase representation, it's available. So you can choose your own phase technologies. Frequency, totally up to you. You can determine your frequency. You can feed in your own frequency. You want to work on a 50 hertz unit, it's okay. You want to work on a 60 hertz unit, it's also acceptable. So you can design accordingly, right? Network representations. You can represent your network in various aspects. Like if you have a very wide scale of widespread of the network, you can just represent it by dots. And thereby you can, what you can do is that you can basically summarize the entire system into a very small grid, representing in the form of dots, in the form of circles. So that makes your work really easier. Powerful network diagrams and graphic visualization features. As I already told you that you will be having visualization features, you'll be having blocks, which you are going to pick and place. So that makes your work really easier. Single and multi-user environment with full support of team working, user accounting profiles, and flexible customization. So as far as flexible customization is concerned, I have given you enough material into it. Let us throw some limelight on the team working part. So once you're buying this license version of this PowerFactory, you are always asked whether you want to go for single user or you want to go for multi-user. Suppose you are using it for your own study purpose, obviously you can go for a single user purpose. But if you want to have it for your organization, for your institution, like you want to have it for JNEC itself. So in that case, you have to go for your multi-user. So you have that option as well. You can work in a coordination system. Like suppose if I am working on a project, I can work on the main grid system, whereas I can assign my co-partner with some work that he will be working on the grid lines. And finally, I can merge both the projects. So these features are readily available with your software. Unique data management concept, including project versioning, that is basically the project versions that I talked about earlier, and archiving mechanisms, master derived concepts. That is why derived concepts, because suppose you have an entire project and now you find that out of this entire grid, I just want to have an analysis on a particular part of this grid. I do not want to work on the entire grid. And if I do not want to work on the entire grid, why should I go for the entire simulation? It's time consuming, right? So I can work on a part of it. So derived concepts are always acceptable out over here. Apart from that, you have unlimited possibilities for process optimization based on integrated and scripting functionality. So if you want to go for scripting functionality, you have a script option over here. You convert the entire build-up that you have built and the entire schematic that you have arranged into a script format. So we being electrical engineers, we generally do not do it because scripting always becomes difficult for us. So we try and avoid the same. But if at all needed, at some point of time, you can easily go for the scripting functionality. It has a feature of the same, right? And apart from that, you have a rich interfacing and system integration options. So this system that you are designing, you can easily integrate it with your SCADAs, that is supervisory control and data acquisitions, your energy management systems, and your grid integrated substations, your grid integrated study systems. So if you have a third-party software as well, apart from DLGSilent, you have a third-party software whereby you want to integrate both the softwares. This is easily integratable. That means what? Suppose I want to monitor and control through SCADA, but I have done my designing on DLGSilent. Like suppose I'm knowing about DLGSilent, I'm doing the designing over DLGSilent. But your end user, suppose I give it to your Tala project. You have a project at Tala. I design it over the DLGSilent and I give it to your Tala project. Now at Tala, if I give this particular integration system, they will perhaps not be very much familiar with. So in that case, what they will say, sir, I want this system to be represented on SCADA. I want the fault detection on SCADA. I want the monitoring on SCADA. Done, accepted, sir. You can do it. Sir, I want the entire report on my own energy management system that I have taken from Honeywell. Done, sir, accepted. We can integrate the systems. So that is a very powerful tool that you have with your DLGSilent. That multi-platform working is always possible. Cross-platform functionalities are provided with your DLGSilent. Professional support via customer portal or hotline, as well as continuous product maintenance and development. That means what? Once you buy this particular licensed software of DLGSilent factory version, what you can do is that is your PowerFactory version. What you can easily do is that you can always have help from your or assistance from your DLGSilent team. So that is a feature that everyone has to give nowadays. If you don't give, they won't buy our product. Right. Now moving on to the applications. Moving on to the applications of PowerFactory. If you talk about the applications. So if we talk about the applications, we can always find that we have already started with generation, transmission, and distribution. So this GTD concept has to be a mandatory part of your PowerFactory. In this, if you talk about your generation, as I have already said, you can always mention the power capacities of your generating unit. Generally, we go with the synchronous type of a generator, and you can go and you can specify the ratings out over there. Once you have specified the ratings, then we move into the transmission part. So before moving into the transmission part, you will be needing over there your buses, and after your buses, you will be needing transformers. In between the buses, obviously, you will be needing some isolators, you'll be needing some protection units. So all these are readily available, and you just need to mention the ratings. Right, but yes, the ratings have to be correct. Until unless the ratings are correct, your simulation ought to go wrong. And finally, we come to the distribution part, that is the power distribution part. Again, with the step-down transformers arranged over there, we will be having our isolators, we'll be having our circuit breakers installed over there. We'll mention the ratings of the circuit breakers, and accordingly, the functionality is going to take place, and we'll be having our GTD system arranged. But now, when I talk about distribution, we have two types of distributions, right? One is the primary distribution, and the other is the secondary distribution. So primary distribution, we generally mention our high-end loads, the high-end loads that we take it to be your primary distribution. Like if I talk about in your own country, in Bhutan, if you look into, for pendant cement, you have a separate line over there, you have a separate substation over there, right? You have a separate unit, you have a separate substation which has been installed for supplementing the power requirements of your pendant cement that is in Gomtu, Bhutan. Apart from that, you have another juice factory, that is your group products that you have. Though you have some outlets out over here in Funsuling as well. But apart from that, you have the main subsidiary out at Samsi, Bhutan. So at Samsi, Bhutan, if you go, over there also you are going to find a separate grid substation for the same. Not only that, a part of the power that has been transmitted from India, they have a line from India as well. Like if you talk about your Funsuling out over there, you have a local substation at Hashimara from where you generally go for the transmission. Right. If you talk about Gomtu, you have a local substation out over there at Birpara, and from there you have the 132 kV lines going to your Bhutan. You talk about Samsi, you have a local substation, a very local substation at Chamorchi, and the main substation at Banarhat. So these are the various positions where you are having the substations, and there is an integration that is taking place. So these local substations that are being meant for your special industries out over there in Bhutan are basically your primary distribution stations. And these primary distribution stations are feeding the feeders to your industries. And in your industries, again, you have a very vast distribution of the feeders. Why? Because you have a classification of the feeders. Somewhere you will be having your PCC type of installations. You will be having your MCC panels. You will be having your APFCR panels. Right? So these different types of panels have to be given with different arrangements, with different feeders, with different power requirements, with different production units. The ratings have to be different. The contactors that have been used on those panels have to be different. If you are going with a high rating, a very high rating of low voltage unit, you might be using your MCCB instead of MCB. Even if you go for higher ratings, you might go for your ACBs, that is air circuit breakers. So these classifications has to be made in a very vivid manner. When I am studying into my distribution system, I am taking my distribution system as a whole. I cannot be very much specific about the end feeder products at my industrial level. So for that, I have to again have a separate system that I have to design, and that is said to be the industry-based system, whereby you have separate lines for your power control unit, you have separate lines for your motor control unit, you have separate lines for your automatic power factor control and rectification units, whereby even if you are going with the capacitor ratings, the series capacitors that you have connected for power factor boosting, that are also mentioned in this particular system diagram. So that is why your industrial systems become that important. And apart from this entire flow diagram, there's another part that we'll look into. Generally, all these big units have their own power plants, small unit of power plants, and that is for local power generation. That is said to be their captive power plant. Captive power plant. The reason behind this captive power plant we'll be discussing in the later slides. So this is the captive power plant. Renewable systems. Now it is very much in like popularism. Why? Because nowadays we know that the non-renewable resources or the conventional resources are just going to be extinct within some years, and we are totally being dependent on the renewable sources like wind, solar, and many other like biogas, your tidal power, as per the locations that they depend, right? So if you are going into a renewable system unit, again you have to look at the various aspects of it. So here is the renewable system study that is a part of your DLG software itself. The distributed systems. That is basically the grid connections. I am producing solar energy at my local unit. I want to connect it to the grid. The grid is having the AC mains. So how can I connect it? And if I am making the connection, whether the connection is viable, whether my total arrangement is okay, it is perfect. In order to check it out, you have to again have this simulation done on your DLGSilent PowerFactory. Basic functions and integrated features. We have the integrated features out over here. Like these are the basic functions that you find with any DLG version. Any DLG version that you will be using, you'll be finding this basic things out over here. First will be your load flow analysis. Very important for any power system study. Without this, the power system study is nowhere. It stands nowhere. So the load flow analysis has to be done in a very formidable manner. Short circuit analysis. Yes, we have to have a short circuit analysis of our lines. Distribution factors. If you are going for distribution, you have to see the distribution factors out over there. There is a medium voltage and the low voltage network analysis. We have to obviously take into consideration. Power equipment models, network representation, network model arrangement, network diagram and graphic features, results and reporting. The report has to be generated, otherwise the analysis is of no use. Data converter. That means what? The data should be converted to the readable format, because we are over here representing in the form of graphics, and whenever we want the report, we want it in the form of a data, in the form of values, in the form of numbers. So that is why we have the data converter out over here. Then if you look into the advanced features, you have the contingency analysis, you have the quasi-dynamic analysis, network reductions, protection functions, arc flash analysis, cable analysis, power quality and harmonics. Some of the terms will be familiar to you. Some of the terms might be a bit foreign as per the students are concerned. See, we have a limitation of time. I cannot go with each and every term. Like if I want to give you a basic idea, the basic idea lies with two terms. That is, first of all, it's productivity. It's productivity in terms of like your outaging, and at the same time, the other part is your reliability of the system. So we are basically concerned with these two factors: whether the system is reliable, and at the same time, whether it has outages. Right, on these two important concepts, we go with this advanced feature analysis. We go with the advanced feature analysis. So far, so good. I hope things are okay. So just to have a small interaction with the students, may we come up with some of the load flow analysis theorems, or some load flow analysis basic models that we generally use, or the methodologies that we use for load flow analysis? Can I have some prompts from your side, students especially? How can we go for the load flow analysis? The various iteration methods. You might have heard about Newton-Raphson method.
Yes, sir.
Gauss-Seidel method. Newton-Raphson method, Gauss-Seidel method, fast decoupled method, decoupled method. So these are the various methods through which we are going for our load flow analysis. And what do we get at the end? What is the main thing that we are getting at the end? We are trying to have a basic report generated whereby we want to see whether my system is in a stable state or not, whether my system is in a healthy state or not. Right. So that is why we go for the various analysis. And whenever you go for this analysis, what is the unit in which you mention all the electrical parameters generally? What is the unit in which you try and mention all the electrical parameters?
Per unit system.
Per unit system. Very good. It's a per unit system. And if you are mentioning it in the per unit system, in that case, what is happening? We have two things into it. How do we get the per unit? How do we get the per unit? What is the basic formula for getting per unit? Like suppose I give you an electrical parameter, voltage. I say V per unit. right? V per unit. So if I call it to be V per unit, in that case, V per unit is equals to VPU is equals to,
V actual divided by V base.
right, sir? V actual divided by V base. One is actual and the other is the base. Two types over here. One is the actual, other base. To get the per unit. Now let us discuss it very fast. That to talk about the various electrical quantities that you come to here in your actual values. First of all, you'll be having, as we discussed, it is voltage. Apart from voltage, you'll be having current. Then you'll be having your resistance, your reactance, impedance. Then you'll be having your active power, your reactive power, apparent power. Did I miss out something? Did I miss out something? I do not think so. I mentioned almost all, isn't it? Now let us come to your base quantity. Let us come to your base quantity. If you talk about base quantities, what are the various base that you get in your while solving your numericals also? Suppose you are solving a numerical, you find that there is a base value mentioned. What are the various base values that you get? What are the various base values that you get? Do you get base values for all this that I have mentioned? I hope I'm audible, is it? Please, students, try and be a bit interactive. This is for you. This is for you that we are organizing the sessions. So try and be a bit interactive. So that gives us the idea that how much knowledge are you having and how much we need to grow on that. Please. So you might have heard about Z base. You might have heard about your V base. You might have heard about S base, right? These are the various base quantities that you generally have. Have you ever, yes, Z base is there that I have mentioned. So, suppose, have you ever heard about, sir, this is my resistance base or base resistance. This is my base reactance. So this is my base active power. This is my base reactive power. No, never. These terms are totally wrong in our power system. This cannot happen in our power system. Why? Because whensoever you talk about per unit conversion, let us now come to the per unit conversion. Suppose you want to have active per unit, that is P per unit, active power per unit, P per unit, PPU. So for PPU, you'll be giving the formula as what? Sir, it's your actual power, that is the actual active power, divided by the power, that is the base power. Now base power is always S base, right? S base. And if you're taking, like, if you talk about power as well, like let us be very common with this apparent power itself. If you go with apparent power, that is apparent power per unit, S per unit is equals to S actual divided by S base. S actual divided by S base. So S actual is equals to what? P actual plus J actual, JQ actual rather. P actual plus JQ actual divided by S base. Divided by S base. So if you are trying to break it off, in that case, you'll be having what? P divided by S base, that is basically P actual, sorry, P per unit, plus JQ actual divided by S base, which is actually your reactive per unit. So that is why whenever you talk about base quantities, it will be the apparent power that will be acting as a base quantity, and never you will be having active power or reactive power as a base quantity. So the same thing goes for your impedance as well. Now, we are moving into the scenario of a DLG PowerFactory 15.1 version. Where I'm using the 15th version of the same. And over here, you can see that they have given us a scale that is of 2 kilometer. That is every per unit is representing your 2 kilometers. I've just taken snapshots, the screenshots of various projects that we have with us, right? So this is basically, if you see, we have taken an MV model basically. That is a medium voltage model. Over here you can see 4S written over here, S, and S. This S basically represents your substations. So this is the overview of the entire model, and your entire grid has been represented over here, and the entire grid has 4 substations. Not necessarily that all the substations are for the same purpose. Might be out of the lot, one might be a generating substation, the other might be a transmitting substation, might be two are the distributing substation, local distribution substations. And these various colored dots that have been represented, these are basically your node representation or your end load representation and feeder representation, and the colors are because of the power consumption. This is basically the color. If you look into the color legend, I hope you understand the legend, right? If you look into the color legend, you will be getting as to how it has been bifurcated. So this is the overview of a project. Now this project, seeing this, you cannot understand anything, you cannot analyze anything. So what has been shown over here? Now let us move inside it. Let me click on one of the substations, right? So this is one of the substations that has been represented out over here. The basic model of one of the substations. Now over here you can get some idea. Sir, here are the here are my bus bars. In between, I am having a bus coupler for coupling the units. Like if I see over here, let me have a pointer. So I'll be having some coupling unit out over here, right? And at the same time, I'll be having further bus systems out over here. I'll be trying to reconnect this, and this will be my end feeders. This will be my end feeders from the substation, which are going forward. So this will be giving you a representation, a graphical representation, a pictorial representation of the real-time view. The first diagram didn't show you anything, right? Now suppose in this also you want to say, sir, these nodes that I have created, I want to study one of the node. Fine. For that, what I have done is that I have taken one of the nodes, one of the end nodes that were represented in various colors. I took that, and you saw over here that you can see over here it is represented in green, right? You have the load terminals out over here. Why? Because all have been represented as load terminals. Because till now we are not ascertained about what is the load, what is the final load, and what is the quantity of the final load that is connected. You are just giving the maximum level, the zenith level of the loads that these lines can carry, right? And based on that, we are making the entire permutations. Because see, we are studying a grid connected system. Now, when you are making the grid, when you are simulating the grid, you can never analyze, sir, what will be the total power connected to it. Once we make the lines, we connect the lines physically, we take the lines out over there, then we can see that how much load has been connected. So we go with the maximum ratings as per the convention. Now over here, you can see that entire representation is in green, and the legend is given over here for the voltage levels. Why is it in green? Because this is a 63 kV unit. This is a 63 kV unit, and that is why it is represented in green. Now I want to make some manipulations. I should make some manipulations. So for making the manipulations, what I did is that I wanted to change the bus bar value. Now see the next slide, what happens. Please try and remember it, have a view of it so that you can hold it back in your mind. And let me move to the next slide. Right. Now see what have I done. I have changed the bus bar values, which was at 63 kV. I have manipulated it, and I have changed it to 20 kV. Once I changed it to 20 bus bar arrangement, standard of at around quite hard. It's quite possible. And since it is not possible, so that is why you can see on my screen it is written as DLGSL, that is really for the silent indication, slash ERR. This ERR shows that there is an error. This ERR shows that there is an error in the system. And once you have an error, you cannot make any further simulations. Right? So why did the error? Because I didn't give it to my bus bar. The arrangement of the bus bar was of the load feeders connected to it was according to 63 volts, whereas 63 kVs, I beg your pardon, 63 kVs, whereas I designed my bus bar as per as 20 kV specifications, which is totally wrong as per the power system concepts. Now, when I transformed it, when I made it pakka, when I made it okay, that I have made the system as per the specifications, that is 63 kV and all, everything is fine. And since everything is fine, so you can see some tools out over here. I'll try and show you my output analyzer through which I can analyze various outputs, right? And this feature gives you the output data, whereas this feature gives you this key gives you the entire representation of your grid. So this is for your grid representation, and this is for your study data representation. Study data in the sense the report that has been generated. The report that has been generated out over here. Now you can see the report out over here. So it is load flow iteration 2 and 3. So you have one. The software has performed 3 iterations. The software has performed 3 iterations. It is giving you a total analysis of the system. Over here, you can see that the maximum loading of edge element is at 100%. Maximum loading you have given up to 100%. Permissible loading is up to 100%. If you want to reduce it, that is as per the data that you have fed inside. Lower limit of allowed voltage, that is 0.95. That means what? You are giving a 5% tolerance to the system. Since you are giving a 5% tolerance to the system, so lower limit of per unit comes to 0.95 and the upper limit goes to 1.05. Under standard conditions, you will be taking it to be 1 per unit. 1 PU will be the representation. That is your actual and base quantities will be taking it to be same, and you will be going for the manipulations. But you'll be obviously having a tolerance, and the tolerance in the system is of 5%. Now see, we are going with the, as I told you that we will be using the tools. You can see over here that the target voltage is of 1 per unit. I'm just showing you the values inside it. That is 1 per unit. Delta limit is -5%. Priority has been set to be -1, and the maximum voltage is 1.05, whereas the minimum voltage is, why maximum voltage? Because the delta maximum tolerance will go to 1 per unit plus 5% of 1 per unit, that is 1.05 per unit. I hope that calculation is clear to you. And minimum voltage when my line is not operating, obviously it will be 0 per unit. So that is the load flow that we are feeding from. This is the basic data. You are just giving load, the line feeder that you have just seen in your diagram. You have given a particular name to it. In the load flow, the advanced part has been shown over here. That is the input method. If you look into the input method, it has been shown as P cos phi. Now, what is this input method? When you study your power systems, you study various types of buses into it. You might have studied about the PV bus, that is a generator bus. You might have studied about the slack bus. You might have studied about your PQ buses. And over here, since it is the direct end load, that we are talking about, over here we'll be taking the bus type to be P cos phi. Why? Because we're just associated with our active power. This is a load. So we are going to, as per the load will run, we are going to pay for it. As per the energy consumption. So that is why we're taking it to be the P cos phi arrangement. If you take it in the case of a bus bar, the distribution bus bar or the transmission bus bar, it is going to be a PQ type. Or rather, you can keep it to be default as well if you want it to be. Now, over here, we have mentioned the power of the load, the maximum power of the load. That is 159 kilowatt. So 159 kilowatt of loading can be done on this particular line. But at the same time, we have inductive factor. This IND that has been written, this is for the inductive factor. Great. What this inductive factor basically shows? Can anyone please prompt? What does this inductive factor basically show? If you have written it as 159 kW and 0.93 inductive, what are you trying to show through this? What are you trying to show through this? If you are writing 159 kW and then thereby 0.93 inductive, what are you trying to show through this? It is basically that we are trying to show that the load is of inductive type of nature, and at the same time, through this inductive, we can find the inductive factor. We can find out our power factor. We can calculate our power factor. This is basically the representation for your power factor part. Whenever you're going for AC transmissions and AC distributions, at the load end, you have to have the power factor taken into consideration. If a power factor drops below a certain level, then obviously the end user has to be penalized. So for that aspect, we are taking our inductive load over there into consideration. If at all you feel that you have a capacitive load, you can change that to be capacitive through the drop-down menu. Fine. So let us go into the next. Let us go into the next part of it. If you go into the next part, this is the minimum voltage drop and maximum voltage drop. We didn't give a voltage drop to the system for the time being. With the voltage drop and the voltage rise, there is the changes, the sudden changes that take place in the system, due to which the transients appear. We have not given any such factors as of for our study. And obviously the optimal power flow. Optimal power flow in the sense, obviously it will be in terms of costing. Right? If you are able to inch out a good costing out of the entire line system, then you will say that for inching a good costing, you have to have minimum of load sheddings. If you have minimum of load sheddings, accordingly the costing will be increased, because less amount of load shedding means more amount of power being used at the user end and more amount of payments to be done, and accordingly your generating unit will be at a profitable level. And last part is the reliability of the system. That is not over here. You can see there's another point, that is the reliability. So it is obviously, if you are designing a system, we'll try to make it as accurate as possible, and we'll try to have the reliability at around 1, that is 100% reliability. And over here we have another system. This is basically for MV system, and we have taken a part of the generating unit out of it. You can see over here it is written as, it's a bit small. Still, if you can manage it out, it's written somewhere over here at my cursor, Wind Park West, right? And over here it is written as Wind Park East. That means what? These are the wind turbines, wind generators that we have integrated with our normal system. To support our normal system, we have integrated some wind power plants over here, which will add on to our entire system. So basically, this is to support our extra load that is being increased. Through this, we can support the extra load. We can have a better load carrying capacity. So that is why we are trying to integrate this renewable energy sources with our existing sources. This is the detailed single line diagram of the same unit. The unit that I shown, this is the overview diagram, and this is basically your single line diagram representation, where you can see your wind power stations as a single line representation. You can see your feeders as a single line representation. So all the symbols have been used, and they have been represented in a single unit. Now again, inside this, if you study one by one, I'm studying the West Park arrangement now. In the West Park arrangement, you can see that name has been given as West Park W1, that is the wind generator 1. You can see over here the capacity of the same has been mentioned as 3.6 megawatt, right? And accordingly, you are going for parallel machines. How many parallel machines are there? There are 3 parallel machines to the unit. That means 3 units are operating parallelly for the generation, right? So these are the basic data that you can study. The active power, as I have already mentioned in the previous slide itself, that is 3.6 megawatt has been taken for the active power generation, and through which you can see over here, local voltage controller is the power factor controller, right? And the bus type is of the PQ bus type, because you have transmission lines, so that is why we have taken it to the PQ bus type. And load voltage controller will be the power factor based controller, that is automatic power factor control based controllers. Minimum and maximum capacities have been mentioned out over here as a range. You can vary the range if you want. This is for your industrial networks, the industrial network arrangement. And the industrial networks, you are not going to find as a generating units connected to it. You will just find the incoming bus bar. You have a main and auxiliary bus connected system. Generally, in all the industries, you have a main and auxiliary, because in any case, the main goes off. You have to operate through your auxiliaries. So these are the 2 bus bars through which the entire load is connected, the feeders are connected, and almost all the end feeders you'll be finding over here as circles. Previously you used to find as arrows, now you'll be finding as circles, because these are the motor loads connected in any industry. And these motor loads are basically your inductive type motor loads. These are your inductive type motor loads. Apart from the same, as I have already mentioned, that you'll be having a captive power plant over here. You'll be having a captive power plant over here, and this captive power plant is just to support the station whenever the entire grid, that is the incoming grid, undergoes a failure. If the incoming grid undergoes a failure, just to avoid the blackout situation, in order to avoid the blackout situation in your system, you generally have this captive power plant inside your big industries, so that the blackout condition can be avoided in case of grid failures. This is the entire detailed study of the last industrial network that we saw, and it has been just clipped from there, and we have shown it over there. Like you can see the tap changes, whether the transformers that have been used out over here have tap changes. Since this is the dead end load in the sense, this is the and in the industrial load system, the last transformer that you have generally does not have any tap changing as such, because inside the industries, if you are working in a 3-phase system, generally you find the lines to be of 11 kV, and the secondary of the transformers to be of around 440 volts, right? So under that configurations, you do not find the transformers. You understand tappings. Tappings are basically to bifurcate the number of turns, and thereby you can have a specific rating of voltage from the secondaries of the transformers. So in small transformers, you generally do not have small transformers in the sense LV transformers. You generally do not have any tappings as such. So over here for the tappings, I have said it to be no. Apart from that, if you see the other terms, it's quite common. So now, let us start with the software part. I'll just quickly give you a minute or so, some seconds. If you have any cross question, you can put it off. And in the meanwhile, I'll be just opening the software. So you can either turn on your mic and you can put your questions. Otherwise, you can put it in the chat box as you wish. In the meanwhile, I'll be just I'll just opening my software. See, when people do not have any questions to be put, it goes to show that either they're too clear with the concepts, and otherwise something is going beyond their head. So I do not think the second one is the condition with you people. So these are the examples. I won't be going into the examples now. I've shown you enough examples out over there through my slides. So I'll be basically going with this itself. Let me maximize it. So this is your entire screen of your DLGSilent PowerFactory 15.1. I'll be creating a new file for you and a new project. So once I open the project, so it's my project out over here. It asks for the name. You can keep it to be grid also, and if you want, you can change the name. These are all up to you options. If you want to change the colors, you can change. As I told to you, if you want to define the frequency of the system, you have the option over here. That is the nominal frequency at which you want to work. I'm working at 50 hertz itself, and this is the normal criteria that we follow in the Indian subcontinent entirely. Right. So this is the demo version software that I'm using out over here, and you can see this is the grid over here. I'm going to make the various connections, and for making the connections, I'm having all the components out over here. So as far as the bus bars are concerned, you can see various types of bus bar arrangements out over here. You can see bus bar circular, you can see bus bar rectangular, you can see junctions, you can see bus bar short, you can see the standard bus bar, right? And over here also you have the double bus bar system, right? So you have all the arrangements of bus bars out over here. It is up to you as to how you want to choose. That is why we said it has a wide range of graphical visibilities, a very wide range of graphical visibilities. Now, apart from the same, if you want to have your templates are over here. You have your substations. As I had shown you in the diagram also, the substation was represented in a circular. So this is the circular substations, this is just rectangular substations, and a number of options. This is your machines, that is your synchronous machine, your asynchronous machine. This is your doubly fed inductive machine, that is double feeding based. Right, over here you have your static generators, over here you have your wind generators, you have your battery storage. So almost all the electrical components that you want to have, you have it over here. This is your load side, again, general load. You have your MV load, you have your LV load, that is the medium voltage load, low voltage load. Right, you have your transformers over here, you have your 3 winding transformers over here. Right, and apart from that, you have your capacitor, as I already told you, for the APFCR panels, automatic power factor control and rectification. You have the capacitors out over here. So almost everything that you need for designing a system is out over here. So let me start with a very small system that I'll be doing. What I'll be doing is that I'll be having a generator bus, and to which I'll be connecting to load buses. So here is my generating bus over here. And let me take 2 load buses simultaneously. So these are the 2 load buses that I have taken, and these are the 2 generators. You have to just click on the symbol and bring it to your grid screen, and you have to click it out over there as per the positions. Once you are done, you can just press escape on your keyboard, and that symbol will not be visible anymore. If you want to see the specifications of the same, you can just click on it, and accordingly you can see now the name is terminal over here. I'll be trying to change it to bus 1 or G bus rather, right? So I'm changing it to G bus. You see the load flow characteristics. We'll be coming to it later on also, but for the time being, I'll be just showing it that it is 1 pu, as I had shown you earlier in my slides as well, right? If you want to change the voltage level, you can, or otherwise it's not mandatory. I'm working with a 110 volt because over here also it is a 110 volt kV system. And now coming to this, I'll be again renaming it. And here is my basic data. And this is now my, I'll just insert a L over here to make it a bit quicker. This is a load terminal, right? Load terminal 1. Okay. And this is my load terminal 2. Load terminal 2. Over here, you can see the load terminals, it is specified as system type is AC. That is your alternating current type. Usage, obviously it is a bus bar. You have taken a load bus bar itself. So it's a bus bar itself. And apart from that, the phase technology ABC. That means what? It is a 3-phase technology. ABC representation shows that it is a 3-phase technology. You can see ABCN, that is with a neutral. You can test 2-phase with a neutral, single phase with a neutral, and biphased. So you have all the types of arrangement as it was there in the characteristics, the features that has been given of the software. Now you can see it at your personal basis, at your individual basis, that yes, we have all the types of arrangements, all the type of phase technologies present with us. Okay. So I'm quite satisfied with the bus bar naming and all. And now I'll be moving to my load section. So obviously I need a generator bus, and for my generator bus, what I'll be doing is that I'll be having a generator out over here. So I'll click over here and I'll just drag it to this particular point. And again, click over here. Thereby, it has been transformed into a generating type thing. Yeah, the representation might be a small now. Once I make it, I will just enlarge it. I'll just enlarge the size for your own understanding. This is my load bus one. There's the load that I'm connecting, and this is my another load that I'm connecting into the other bus. Connected to the buses. Now my thing is that I should have transmission lines to connect. I'm not going for any generators for any transformers things as of now. Just for understanding part, I'm just connecting it directly with the transmission lines out over here. So these are my transmission lines connected, right? So that's it. Now I made the connections. Now let me go for the values part. That is values of your and your loads. Now once you talk about this particular part, that is your load and loads and your generators. Since we are designing a very small part of the system, generally, what your first assumption is, because this is totally probabilistic study, right? This is totally probabilistic study. So in our probabilistic study, we always follow the reverse engineering method. We follow the reverse engineering method. So in our reverse engineering, we'll be starting off with the load part first of all. So let me go to this particular load, and since it will be obviously PQ, and over here I'll be going with, suppose it's a 3 megawatt load, and it's a 1 MVR reactive power, and per unit obviously 1. So I'll make it okay. I'm making a probabilistic study of my second load as well. Again, make it to be PQ. These are my bus bars. Over here, it will be, take it to be 4. And let us take it to be again 1 over here. Okay. And apart from the same, there's a message over here. Fine. So I think I was done with my load part. Yes, I was done exactly. So it's okay. Now I'll be going to this particular part. And over here, again, now this is my generator part. So in my generator part, I am going to make it as, again, PQ. Over here, now I'm making a probabilistic reverse engineering. 3 megawatt assigned to one load, 4 megawatt assigned to other load. I might have some expansion in future also. Keeping that in mind, I'll be trying to have a 8 megawatt generator. And MVR, already it's 1 plus 1, 2. So I'm taking it to 2 MVR for the system. Now over here you can find the max PU and the min PU, right? And the variations and the bifurcations if you want to see. Over here you can see the advanced parameters, that is the capacity curve over here, right? And automatic dispatch, that is the load dispatch, the metric order system. So this will be going into details in the later frame of time. And over here I go with OK. Now I have fed parameters to all the parts of my system, and this is my transmission view. So we are going to the complete short circuit analysis. Short circuit location will be at 50%. That is, and if you see the basic data, terminal I has been denoted. Data has been denoted as terminal I's. Right, that is a load terminal 2. And over here you can find the similarly for other one also. So I have now taken for the timing, I have taken lines to 1 kilometer, right? I have taken the lines to the line is 1 kilometer over. So now, fine. So the entire system is done. The basic load flow analysis. So I'll be going to the output operator as I have shown to you. Let me once of all cancel it. If I was This is my operator, that is for documentation of device data operator. And over here, I'll be operating the load flow. So select it, click on this arrow, it will come to the available functions. Now I can execute the system. Now over here, due to some malfunctioning, there has been some error in the system. There has been some error in the definition to make quickly. Perhaps I have missed out some parameter. There is an error. If all the error has occurred, at any point, you have to again go with the reconstruction of the system, correcting the parameters. So this is how you go with the analysis as to how you pick up the system, you drop the systems, how you make the analysis. You can go, you see the various analysis. Like if you talk about this is your fault analysis, short circuit analysis, and from here also you can study various parts of the system, and accordingly you can go with
Hello.
things.
हेलो
Yeah, hello.
हाँ इसमें ना कुछ वॉइस प्रॉब्लम आ रही है कुछ लोगों को ना मैसेज भी है तो एक्चुअली कई लोगों को है एक बार
अभी
चेक
भी
करिए
है?
हाँ अभी आ रहा नहीं मेरे को आ रहा है लेकिन कुछ लोगों को प्रॉब्लम हो रहा है उधर से नेटवर्क वैसे तो है ना
Is it clear now?
ब्रेक हो रहा है कुछ
If it is
ब्रेक
clear now, I'll just go with the final.
ब्रेक हो रहा है
Is it clear now?
Why?
Is it clear now?
Now clear, but sometimes it's break.
No, let it come from the audience side. Is it clear now?
Audience, yeah. Okay.
Yes,
Not
sir, it's clear, sir.
Now it's clear, right, sir? So let me go with I think the last 5 minutes or 7 minutes we had a small buffering in the network. So not an issue. I'll just take a recall of the system. So what I'll be doing is that I'll be again restarting my software. Great. Okay. You might have seen while I was working on the same, so I don't think there'll be much of a problem with this. So I've just gone with this 3 buses out over here. These are my 3 buses that I have taken. And after I have taken these 3 buses, next will be my generator to be connected to the system. So this is a synchronous machine basically. The synchronous machine can be used as a synchronous motor as well as a synchronous generator. As a synchronous motor as well as a synchronous generator. So these are my loads that I have connected. This is my transmission line. Right, and now I'll be escaping this, I'll be leaving the symbol with the escape button, and I'll be going with my system analysis. Synchronous machine, yes, it is okay. Load flow, it is 8. Reactive power is 2, and rating factor is the max, right? So it is min as 0 and max is 0.9. Fine, it's okay. So it's okay with the same. This is my load. Let me define it to be at 4. This is at MVAR, that is the reactive power is at 1. Okay. This is my other load. This is 3 and this is 1. So my total active power is somewhere around 7. That is consumption is around 7, and your dissipation is around 8. So that is quite balanced, right? And now let me go to this. Let me once check out the load flow part, the execute. And over here, you can see that the data has been generated. The data has been generated. Now, in order to have a look at the data, we'll be clicking on this. This is our maximize output window. So this is our output window. We want to maximize it. So I'll be clicking on it. Now you can study your system out over here. The maximum voltage was 1.05 per unit. The minimum voltage was 0 per unit because it was at 0. Access time, it hardly took any time to access of switches. That is, you do not have any isolators or something as such. So that is why there is no access time mentioned as such. If you had isolators or breaking switches, so in that case, there is a trip time. What we call it to be the trip time would have been mentioned over there. You can see, like we have not changed the commissioning date. So it is from the time the software has been installed or the software is existing. So it is from 1970s that they have given until the current date, that is 1/6/2020. And it is as per my local timeout over here, that is 30826. As per the BST, if you are working according to the Bhutan Standard Time, then in that case, it will be half an hour later. And apart from that, the latitude and longitude, because we have not mentioned any place in our grid system, so lat long has not been mentioned over here. Once you take the lat long, it will be also out over there. And accordingly, you find that your system has been defined. All the parameters. You are working on a 110 kV line. So over here, you have the 110 kV line. Let me start it from once from the starting itself. That is, your transmission lines were of 1 kilometer, which I had already mentioned to you. Derating factor, that is the degradation factor, derating factor that we have taken, it is of 1. Short circuit at location that I have shown to you, that we are measuring at 50% location, that is at 0.5 kilometer. Maximum loading, we have given a maximum loading of 100%, so not an issue with the same. And apart from that, if you move into the other parameters, that is my load parameters if I talk about. So let me scroll it a bit. And this is the ambient temperature at which we are going to work. So it is 20 degrees at which they have taken it to be working. Beyond 20 degrees. And accordingly, what happens is that the depth of laying, if you change the temperature, the ambient temperature, if you're going to change over here, not over here, basically in your project, if you're going to change. So in that case, the depth of the laying of the cables, because we have taken an underground configuration over here. We have taken an underground configuration over here. So in that case, I will be showing you where we have taken it to be underground. We have taken it underground configuration. So it is 0.8 meters below the ground. And if you take it as overhead lines, again, the specifications are going to change. So you can see out over here. Zones and areas, we have not mentioned anything. It is by default I and J. So zones and areas have come to be 0. Out of service, both the feeders were working. You have assigned load to both the feeders. So it is none of the feeders are out of service. Both the feeders are working. Parallel lines, you have only one parallel line. Only one generating unit was there. So the number of parallel lines will be only 1. If you connect more than one generating units to the same bus, then you will be having more than one parallel lines. So this was the brief analysis of the report. Now I'll be going back to my system. So you can over here maximize the graphics window. This is my graphic window that I call it to be. There is my grid window. And over here, you can see if you move into the transmission line part, over here I'll be showing you that is laying. Laying is ground. So it was 0.8 meters below the ground. You have other options as well, that is in the air, that is the overhead. So if you choose overhead, again, the specifications are going to change. Derating factor, it was mentioned over here 1, so it was shown in a report to be 1. Length was taken to be 1 kilometer, and the short circuit was at 50%, so it was shown to be 0.5. Now suppose over here you had many data to club together. If you do not want all the data, to be represented, so in that case you have another option. Suppose you want to only have the short circuit analysis of this particular line. So you can choose this line. See, this line is chosen. Once you click on it, it will be chosen. Go over here. Over here, you can go for the complete short circuit analysis. Choose it. Be sure that no other parameters are chosen. Like suppose if you do as such, now this is a mistake. This is going to generate an error. So please do not do that. Only choose the complete short circuit analysis. Number of decimal places that you want to have after the decimal is 4. You can reduce it. That is up to you. And over here, you can have execute. Right? So this has been executed, and since we have the entire report, so no different report is going to appear as such. since already we had the short circuit analysis already generated and we didn't change any values. So the same report is going to remain as such. But if you want only short circuit analysis, that is the way as such you can go for the short circuit analysis. Right. So through my small presentation, I try to show you the various aspects, and along with that, I also try to brief you up about your load flow analysis and your short circuit analysis, and try to design a small system at your DLG end. Now, I hope you might have got a basic brief idea of the software. Though I'm very sorry that the session extended 15-16 minutes. That was the information that I was trying to transfer in the due course. I extended the time. I'm very sorry if I have disturbed your evening routine. But it was anyways a nice interaction with you people, and good to see that beyond time also I'm having around 20-22 participants waiting for more informations. Thanks very much for your cooperation from your end. And if you want some further information, some further knowledge, some further emphasis on this particular part, so you can always come back to me. And I hope we have a good Nepali crowd over here, people who understand Nepali at least. नेपालीमा पढ्नुलाई खोजेपछि नेपालीमा पनि पढाउन सक्छु, नेपाली पनि आउँछ, तो त्यही लागि अप्ठ्यारो छैन. Rest, I think if you have something to share, I'll be waiting over here for some time. So you can always share it back to me. If you have any reviews or anything as such, your reviews are always welcome, and we try to improve. Thank you, sir. Thank you all. And if anyone has any feedback from your side, please share it with us. And something in addition, if you want from my side, like if you want some sessions on MATLAB, or if you want some sessions on power panel designing, your control panel designing, will be eager to serve you out. And these are the basic things that the students require nowadays, because even if you see in Bhutan also, you have a lot of potential for all these fields. People who are being hired in this idle projects, people who are being hired at your cement factories, at your juice factories, they also need these basic estimations and graphic calculations. So if you look anything as such, if you look for anything as such related to power systems and anything, you can always contact me up, and I'll be like always ready to serve you up. You always have Mr. Lalit's and Mr. Navraj's number. If you want my number from my end, I can just share a number. So thank you very much. Thank you all. Have a nice evening. Enjoy your day. Hope to see you soon. So I hope I can sign off.
Okay, thank you everyone, and have a nice day. Yeah, see you.
एक बार करना जरा